So our M2, which is the negative hugging moment, will be equal to, so we are using the formula we used previously. So 9 on 128 multiplied by GK, which is the characteristic permanent action, multiplied by the span squared, plus 49 on 512 multiplied by QK multiplied by all squared. So let us go ahead and slot in the values. So we have 9 over 128. So the permanent action is 10.6, and this time around the span is 6 raised to the power 2 plus 49 on 512 multiplied by the characteristic variable action, which is 3.75 multiplied by 6 raised to the power 2. And if we work this out, we will have a value of 39.75 kilonewton meter per meter. So that is the value of our moment, the negative hugging moment. So in the next step, we are going to distribute or apportion the moments that we've computed. That is the maximum hugging and sagging moments within the supports and the spans. We are going to distribute them into column and middle strips. And this provision is clearly outlined in the Eurocode 2. And we'll be using a method called the equivalent frame method. Later on, we would also look at how to divide the slab panels into column and middle strips. So let us head on. So the next step, that will be the fourth step. So let's call that distribution of moments into column and middle strips. And we are going to consider the moments in the X direction first. So moments in X direction. So as mentioned earlier on, we'll be using the equivalent frame method as outlined in Eurocode 2. So the table as seen on the screen is obtained from Eurocode 2, and it shows how the moments will be distributed into the column and middle strips. So as seen for negative moments and then considering the column strips, so you can distribute between 60 to 80%, and for the positive moments, you can do 50 to 70%. Again, for the middle strip, and then considering the negative moments, you can do 40 to 20%. And for the positive moments, you can do 50 to 30%. But in our design, we'll be doing mid of these values. So we'll be doing 70% for the column strip, that's negative moments. And then we'll be doing mid of this, which is also 60%. And then we'll be doing 40%. Yeah, so this is what we'll be using for our design, just to make it conservative. You can use the lower limits. In this case, that will be 60% for the column strip, and the upper limit will be 80%, but we are using mid values. We are using mid percentages, right? Again, before we go ahead and compute the moments that will be developed in the column and middle strips, let us look at how to divide the slab into column and middle strips. Again, from the equivalent frame method, this is the principle. So in order to divide this slab panel or B into column and middle strip, we need to consider the LY direction, right? One of the spans in the LY direction, and then we'll divide it by 4. So for the column strips, we'll divide it by 4 for the column strips. So let us go ahead. So I'm just drawing it without dimension. Later on, we'll draw it to scale in AutoCAD to get the dimensions right, but this is just for explanation purposes. So let us divide this side. So that will be our first column strip. The second one will be the vertical direction. The next one also be a column strip. That is also another column strip. And again, they are internal columns, so we need column strip there. So the dimension that we've done here, so this dimension is LY over 4. So it means that the LY, which is the 6 meters, divided by 4, that will give us 1,500 or 1.5 meters. So that means that this dimension here is LY over 4, which is the 6,000 divided by 4. That will give us 1.5 meters. And it's the same throughout. So this dimension is also LY over 4. So the width of this column strip again is the same, 1.5 meters, because it is LY over 4. And then again, if we consider this column strip is the same 1.5 meters. That is the column LY on 4. It's the same at the bottom here, right? So again, let us consider the column strips for the internal columns. So we'll have another column strip here. So that will be the column strip for the internal columns in the vertical direction. From the edge of the column strip to the center of the column is ly on 4, and then the same as the other side as well, ly on 4, which is the same as, which is 1.5 meters, and this is also 1.5 meters. Now let us consider the column strip in the horizontal direction as well. The column strip is in both directions, similar to what we did for the peripheral columns. So we have it in the horizontal direction and then the vertical direction as well, right? So wherever we have the columns, you would have a column strip in there. So we'll have another column strip here. Again, the dimension for this column strip, that is ly on 4. This is also ly on 4. So our ly is this 6,000. So our ly is 6,000. So that will give us 1.5 meters and 1.5 meters. So the overall dimension for the column strip will be 3 meters. And the same applies to this side as well. So that will be 3 meters. So this is our column strip. Let's label it. So this is column strip. Okay. This is also a column strip. This is also a column strip. Again, the sides as well and this side as well. Now in between the column strips, we have what we call the middle strip. So that is also a middle, right? So now let us go ahead and distribute the moments into the column and middle strips. So first of all, we are going to consider the column strip, and that is the negative moment, and we'll be using 70% distribution. In order to compute the distributed moment, we are going to apply the yield line theory to compute the negative moment or the distributed moment within the column strip. So let us call that moment MCN, right? So that would be equal to, so the moment, which is the negative moment we computed earlier on. So this negative moment, so the minus 100.9, and then multiplied by the percentage. So we are using 70%. So 0.7 multiplied by the ly, which is the 6 meters. Again, multiplied by 1 on the width of the column strip, and that is x direction, so that is 3 meters. So if we work this out, we'll have a moment of 141.3 kilonewton meter per meter. So that is the column strip. So let us go ahead and do the middle strip. Again, we are considering the negative moment. We are using 30% distribution. So again, using the yield line theory, we'll compute the moments as, so let's call that moment MN. So that will be equal to the moment, the same negative moment. So 100.9 multiplied by the percentage distribution, right? So that is 30. So 0.3 multiplied by the span, the ly, which is 6, multiplied by 1 on the width of the middle strip, right? The width of the middle strip in the x direction, and that again is 3 meters. So if we work this out, we'll have a moment of 60.54 kilonewton meter. So let us continue now and do the positive moments. So again, we'll consider the column strip, but this time we'll be doing the positive moment, and then the middle strip will do the positive moment. Then here we can compute them here. So column strip and positive moment, okay, and we'll be using 60% distribution. So let's call that moment MCP, and from the previous formula we used here, so that will be, and this time we are going to use the positive moment, right? So the sagging moment we computed here, so the 62.1 multiplied by the percentage, which is 0.6, multiplied by the span, which is 6, multiplied by 1 on the width of the column strip, which is 3. So if we work this out, we will have 74.52 kilonewton meter per meter. Again, let's consider the middle strip, and this time the positive moment. So middle strip, positive moment. we'll be using 40% distribution, right? So again, let's call that moment MMP, and that will be equal to, so the moment, the positive moment is 2.1 multiplied by the percentage, which is 0.4, multiplied by the span LY, which is 6, multiplied by 1 on the width of the middle strip, which is also 3. So if we work this out, we'll have a moment of 33.12 kilonewton meter per meter. So we've been able to compute the moments that will be distributed to the column strip and the middle strip. So that is for the X direction, the moments in the X direction. So we are going ahead and do the same for the Y direction, and again the negative, and we'll be using 70% distribution, just like the moments in the X direction. So again, using the yield line theory, and let's call that moment MTN. So that would be the moment right in the Y direction. Let's go back and look for the negative moment in the Y direction. So that was minus 64.7. 64.7 multiplied by the percentage, which is 0.7, multiplied by the span. In this case, the span is 7.5, multiplied by 1 on the width of the column strip, the width of the column strip in the Y direction. That is also 3 meters on 3. And if we solve this, we'll have a moment of 113.23 kilonewton meter per meter. So that is for the column strip. Again, let us look at the middle strip, then we'll consider the negative moment. We'll be using 30% distribution. So let's call that moment MMN, and that will be, so the moment here 64.7 multiplied by the percentage 0.3 multiplied by the span LX, which is 7.5, multiplied by 1 on the width of the middle strip, right, in the Y direction, and that is 4.5. So multiply by 1 on 4.5. Again, if we work this out, we'll have a moment of 32.35 kilonewton meter per meter. So let us go ahead now and do similar for the positive moments. So column strip, and this time we are doing positive moment. We'll be using 60% distribution. So let's call that moment MCP. That will be equal to the moment. So let's go and look out for the positive moment. So that is 39.75. Moment 39.75 multiplied by the percentage 0.6 multiplied by the span LX, which is 7.5, multiplied by 1 on the width of the column strip, which is 3. So if we solve this, we will have a moment of 59.6 kilonewton meter per meter. And then finally, let us do for the middle strip. So middle strip, and we are considering the positive moment. So we'll be using 40% distribution, right? So let's call that moment MMP, and that will be equal to, so the moment, which is 39.75, multiplied by the percentage, which is 0.4, multiplied by 7.5, multiplied by 1 on the width of the middle strip, which is 4.5. If we solve this, we would have a moment of 26.5 kilonewton meter per meter.